Dear learners, welcome to week 4, lecture 1. Till now we have discussed that in the first week I have covered that the basic concept of composites. In second week I have developed that theory of surfaces, in which we have obtained that Gauss theorem and second fundamental theorem of surfaces and other derivatives of normal and tangent vectors. In the third week we have started that how to develop a governing equation for a doubly curved cell. We have derived that from the basics by assuming a first order displacement field that u is equal to u10 plus xi times psi 1, u2 is equal to u20 plus xi times psi 2, and w is equal to w naught, where transverse displacement is constant along the thickness. So, using those displacement field we have developed the basic governing equations of shell in curvilinear parameters alpha and beta. That alpha and beta are orthogonal curvilinear parameters, and we also discussed about that special cases that from the basic shell equations can we get that equation of cells for a cylindrical shell or a spherical shell or a conical shell or a plate or a circular plate. In today's lecture I will discuss that how to proceed further once we get the governing equations, and now what are the steps so that we can get the solutions. Ultimately we are interested in the displacement and stresses moments of the shell subjected to loading and boundary conditions. So, these are our basic governing equations of shell, in which we have taken the nonlinear terms as well as linear terms. So, we developed that these 5 set of governing equations can be solved in this form. Can we get the solution of a cell subjected to boundary condition, whether you talk about just simply a circular cylindrical shell, if you convert to that equations, can we get the solution in the same form? No, we cannot get the solution in the form, because we have our unknowns are in terms of displacements u10, u20, psi 1, psi 2 and phi. We have these 5 primary displacement. So, we have to convert these equations into the primary variables u0, u10, u20, psi 1, psi 2 and w0. So, how do we convert this? So, we use that cell constitutive relations. So, I have also given that linear cell equations, that in most of the cases even itself the linear cell equations are complex to solve or difficult to solve. So, even containing the nonlinear terms, it makes further difficult to solve. So, analytically or in lecture point of view, our aim is to solve at least to you that explain the basic steps, how do we solve a linear equation, and then later on that nonlinear problems can be solved. So, for that we need the cell constitutive relations. So, you may be aware about the generalized Hooke's law, which is this, or vice versa, that epsilon ij equal to Cij KL epsilon KL. So, sigma ij, so this is the just reverse relation. So, for a purely mechanical cell, means elastic shell, that epsilon ij is equal to capital S, I, J, K, L, sigma K, L, where S is known as compliance matrix and here C is known as stiffness matrix. This we are aware that is available for a orthotropic material. Why we have chosen to orthotropic material? The topic of our shell is that composite, that shell is made of or a composite cell or a sandwich cell. Generally that if we talk about a graphite epoxy cell or a glass epoxy cell or any other kind of composite material, they are generally orthotropic. So, metal properties are orthotropic in nature. So, we have chosen that a orthotropic matrix. If we have chosen isotropic matrix, then some of the elements will be just a function of first. So, S11, S22, S33 will be the same for the case of a isotropic material. So, we have taken a orthotropic material and this is the three dimensional relation available for a material where strain can be expressed in terms of stresses using this compliance matrix, plus we have also taken a thermal. So, sometimes we want to analyze that a composite cell under temperature loading. If we are interested in such cases, then we can include the temperature effect also. So, there for a known temperature we can find out the stress means thermoelastic analysis, basically that is known as thermoelastic analysis of a shell. These theories are developed, the shell theories, that moderately available or gives accurate analysis to moderately thick to thin cells, and the basic assumption behind that what we have developed, that under plane stress assumption. So, under plane stress assumption we assume that sigma 33 is equal to 0. So, there is no stress in the third direction, basically in the if third direction is our thickness direction. The assumption is basically as per the physics we can say that because shell is very thin and because material is less, so it cannot take stress in the third direction. So, by using that assumption we have developed the shell theory. So, if we apply this assumption, if we put sigma 33 equal to 0 here, then these equations are reduced and can be expressed like this. I have just expressed for the mechanical case, even that including the temperature one can write here also B1, B2 and 0 and temperature and so on. So, there is no issue in that. Sigma 11 can be expressed in terms of a matrix Q, where matrix Q is known as reduced stiffness matrix. This is the very standard notations and one can find this type of notations in any book of mechanics of composites or the books on theory of composite plates and cells. In the earlier books of shell in which only the isotropic cells are discussed, so these type of equations are not discussed in those type of books, but the recent books after I think 90s when the composite material has been taken and research has been done. So, in those recent papers or recent books you will find that in books of cell you will find this kind of matrices are available. Now, what is the definition of our in plane stress resultant? Very first definition of N11. N11 is defined minus h by 2 2 plus h by 2, or you can say that zeta sigma 11 1 plus zeta by r2, that radius of curvature in the second direction into d zeta. Now, from here the concept of solution or that based on the theory start changing, that if we say that I want to apply only a very thin shell or very shallow shell. Shallow shell means when you have a radius of curvature is very large. So, when it is thin and it is very large, so this component can be neglected compared to 1. But if you are in that case, most of the thin shell theories book, you will find that this is not considered and N1N is obtained like this, and we proceed further. But if you want to solve a complete shell, that because at any time we can reduce to. So, we are going to solve a generalized shell which can give you the solution for a thick as well as shallow as well as thin. So, all the solutions. So, we will write 1 plus zeta by R2 zeta, this we are going to consider it. Next, what is sigma 11? Sigma 11 is here q11 of epsilon 11 plus q12 epsilon 22 1 plus zeta by R zeta 2. Now, you know that epsilon 11 add epsilon 22. So, initially when we defined the strain components, we have said that it will be a two part, one will be causing the membrane stretching or the stretching in the cell, and second part will cause bending in the cell. So, that terms are clubbed under head epsilon 110 and some terms clubbed under the head epsilon 11. So, these terms called membrane stretching and this is called bending or curvature. Same way epsilon 22 is expressed. Again, this is not even that simplified now, further we need to look in it, that epsilon 11 is what? Epsilon 11 is this much, explicit terms, and epsilon 11 is this, means that bending terms and the stretching terms, where these terms are nonlinear terms and these terms are linear contributions. Here it is 1 by A1 is common. So, we can say that 1 plus zeta by R1, basically 1 by A1, it looks like that A1 1 plus zeta by R1 and inside that. So, we will use that 1 by A1 will take inside and 1 plus zeta by R1 power of minus 1 can be written like this. So, if we take small a1 inside and linear terms plus here it is again a1. So, 1 plus zeta by r1 minus a1. So, 1 a1 is here, again a1 is this side. So, it will be a1 square and the nonlinear term plus zeta times of this, then again a1 xi1 by z2. Now, we can say that this is lack of this term 1 plus zeta by r1 divided. So, we will call it small epsilon 110L. Then this term is also having slightly difference, it is known as epsilon 11NL and this term is known as epsilon 11N hat. So, this epsilon can have three components in which this is your common component 1 plus zeta by r1 inverse and these components can be written like this. So, if we replace epsilon 11, same way epsilon 22 can be written as 1 plus zeta by r2, instead of epsilon 22 it will be zeta by r2. We can say that epsilon 22 of 0L plus 1 plus zeta by r2 minus 1 epsilon 22 NL plus epsilon 22 of hat 1. If we substitute like this, so N11 can be written as minus h by 22 plus h by 2 q1 1 plus zeta by r2 and this is out 1 plus zeta by r1 inverse, and then we will have epsilon 11 of 0L plus 1 plus zeta by r1 inverse epsilon 11 NL plus zeta times epsilon 11 hat plus q12 1 plus zeta by r2 is fine, but in case of N22 it will be 1 plus zeta by r2 minus 1, and the same terms epsilon 2 to 0 L plus 1 plus zeta by R2 minus 1 epsilon 2 to N L plus zeta times epsilon 2 to of n whole multiply d zeta. So, we will have terms like this q11 1 plus zeta by R2 into 1 plus zeta by R1 of inverse. This is the strain part. So, these terms contains some zeta terms, yeah, they will also come. So, at least for the case of this term, this will be the coefficient. For the non-linear, if multiply with, then these 3 terms will be the coefficient. For the case of bending, zeta times will be the coefficient and integrating. So, that coefficient is denoted by some term and it is denoted by capital A1, Aij. Generally in the plate we called it Aij, 2 index, like this. A11 epsilon 110 L. Here index is noted as in about 2 1, and in the case of nonlinear 211. In the case of zeta times it will be B1121, and again Q12 contribution will be A1222, A1222 and B1222. Why we have put that index 21? It tells you that 21 means that 1 plus zeta by R2. 1 means 1 plus zeta by R1. So, if 2 means there is no inverse, first index no inverse, second index means inverse something, and it also tells you the radius of curvature in that direction. So, some here let us say I am not just saying 1 2, it means minus h by 2 2 plus h by 2, maybe something q1 1, or then 1 plus zeta by R1 and 1 plus zeta by R2 will have inverse of that. So, that tells you the inverse kind. When we talk about a nonlinear terms, then it will have 2 inverse. So, if that index 1 1, so 1 plus zeta by R1 inverse, then 1 plus zeta by R1 inverse. B1121 means 2 here, R1 here. 2 2, 1 plus zeta by R2, and second index 1 plus zeta by R2 inverse. So, in this way it is carefully designed so that we cannot miss that A11 means what. In the case of plate, just I would like to, A11 is sufficient because A11 in the case of plate is just Q11 of upon G2. Here we do not need the second index in the top because there are no terms, but now we have these 2 terms. So, you will have the components of N22 components in that N12, N21. So, we may forget that which comes where, that which will be the inverse one. So, it will help us to find out the inverse term properly. So, now we have to find out the definition of a moment. So, definition of a moment is sigma 1 1, 1 plus zeta by R2 sigma 1 1 into zeta. That is the definition of a moment. Now, we can express sigma 1 1 in terms of Q11 and this term and Q12 this term. Already I have explained that what is the meaning of epsilon 110 L, what is the meaning of epsilon 11 NL and epsilon 11 hat. So, we call it 1 plus zeta by R2, zeta times 1 plus zeta by R2 Q11 will be B11 2 1, and here 2 1 1, and this term will be because zeta square. So, whenever a zeta square come up, we denote it as the D, bending stiffness, So, D11 2 1 epsilon hat 1 1. Same way the contribution of Q12 terms. So, B12 epsilon 2 2 2 2. Then 2 2 2 triple 2 B12 in the case of nonlinear contribution. Then the bending contribution D12 2 2. So, now we can define B1121, B11211, D121 and so on. So, we have defined the definition of M11, N11. Now, a slightly different definition is N12. N12 is, we have to first say that what is the definition of gamma 120 and gamma 121. So, gamma 120 have two parts. That first part in which 1 by A1 is common and the second part in which 1 by A2 is common. So, if you remember that when we were developing the cell governing equation, that first part corresponding to N12 and second part corresponding to N21. So, first part, so when we write that constitutive equations for a cell, so we will consider that first part for the case of N12. Definition of N12 is minus h by 2 to plus h by 2 tau 12 plus 1 plus zeta by R2 and d zeta. So, tau 12 is Q66 into gamma 12. Gamma 12 have omega 1 0 L plus omega 1 N L plus omega 1 hat is a bending part and nonlinear part and linear stretching part. We have three contribution. Same way we have a N21. N21 we have these terms W2, W2 NL and W2 hat. W2 linear, W2 NL and W2 hat and 1 plus zeta by R2 Q66. This is our definition of N12 and N21. Now we can say that inside that 1 by A1 is common. So, 1 plus zeta by R1 inverse come here. So, let us see that first term will have 1 plus zeta by R1 inverse and inside that 1 over A1 and again here A1 square will be there 1 plus zeta by R1 and 1 the bending terms zeta by A1 psi 2 comma alpha and d zeta and in the definition of N2. So, first term this will become the definition of A6621 Q66 1 plus zeta by R2 1 plus zeta by R1 inverse, then non-linear part of that plus non-linear part, this will be the definition. Then the bending it is will be denoted by B6621. Same way from the N21 A6612 1 by 2. Sometimes it is taken inside the definition because 1 by 2 is common I think in all the nonlinear terms. In some of the books of shell theories that 1 by 2 is taken inside the definition of omega 1 NL and omega 2 NL, but in some books it is kept outside. So, B6621 and B6612. Can we now journalize? Can we write in an index form? Yes, that we can write in an index form. That very first definition is Aij alpha beta. So, we can write Qij 1 plus zeta by R alpha 1 plus zeta by R beta of inverse. When we have a definition of Bij alpha beta, it will be minus h by 2 2 plus h by 2 Qij 1 plus zeta by R alpha 1 plus zeta by R beta into zeta. What is the definition of D? Inverse will be here and zeta square. Then the definition of non-linear terms A, I, J, alpha, beta, gamma, when we have a 3 index. For the case of non-linear terms, we have 3 index. If you are not considering the non-linear terms, so don't worry. But if you consider the non-linear terms, then it will have 3 index, and in the 3 index, last 2 index will be zeta by RB, zeta by R gamma, and both will have inverse terms. Same way in A there is no zeta, in Bij zeta times of those terms, in Dij zeta square of those terms. So, this is our generalized definition of Aij, Bij and Dij, and point to be noted that Aij alpha beta is not equal to Aij beta alpha, which is obvious because if you say that Aij beta alpha will be Qij 1 plus zeta by Rb and 1 plus zeta by R alpha inverse. So, here the term 1 plus zeta by R alpha is inverse. In case of alpha beta, 1 plus zeta by Rb is inverse. So, they cannot be equal. They will be equal only when you say that your shell is very thin and you are going to neglect these terms R alpha and R beta, then only they will be same. Now, we are clubbing into a matrix form, that N11, N22, N12 and N21. So, there will be a matrix in which have the non-zero components are placed like this. The first component is A11, 21, A12, A22. Here A12, 21 and A22 and A6, A6. So, these will contain the linear the stretching part, and the component B11, B12 will have the bending part of the, plus the green terms are non-linear contribution. So, depending upon the definition, in some of the book half is kept outside, so or sometimes it is kept inside the definition. So, it is just a matter of choice. The point to be noted here that for the case of if it is a plate, then these terms may not exist, that B11, B12. But for the case of shell, all the terms are existing. Now, same way can we represent the couple constitutive relation. This is the in-plane stresses and in terms of strains. Ultimately, when we have to use for the case of solution, we will write it explicitly and solve it. So, but first we have to define like this. It is also important to write like this for a programming point of view, so that if we write a matrix component, that non-zero component of a matrix, and then later on we have to multiply with this. Same way the moment M11, M22, M12 and M21. So, we have to find it out, and we have arranged that B1 D matrix and B11 of triple coefficient 2, 1, 1, 2, 2 exists for a non-linear case. This is for a bending, this is called a stretching and non-linear part. Now, we have left the shear forces Q1 and Q2. So, Q1 and Q2 can be written as A44 and A55, and the coefficient will be epsilon 23 and epsilon 13. Here point to be noted that for the case of first order shear deformation theory, it is multiplied with some Ks or divided depending upon the situation. So, here we are saying a general case, later on one can multiply. So, because that in the first order theory, that shear forces when you evaluate, they do not come so accurate. So, we have to multiply with a factor, that factor is known as shear correction factor. So, based on the geometry and loading, that shear correction factor is evaluated and it is multiplied with that, so that we can get that shear stresses are along the thickness accurate for accurate shear stresses. So, already I have discussed that for a case of thin shell, zeta by R1 and zeta by R2 are neglected, and for the case of shallow shell neglected, but for the case of thick shell it is considered. Now, but how do you solve this thing? This is inverse of that. Ultimately you are writing a program, you need one number. So, this is term like, it can be like that, 1 plus x raised to power of minus 1. So, the binomial expansion of that. So, that will be 1 minus x plus x square minus x cube and so on. So, if we expand that term and it will go to up to infinity. So, this will go to up to infinity. So, based on inclusion of these terms will give you a entirely different shell theory, whether we say that we have to take only the first term 1. The logic is behind that the thickness is small and R1 is large, so this can be neglected. But for the thick shell, so generally as far as I aware that in the case of Flige shell theory, that up to this second order terms are considered in this binomial expansion. So, in most of the thin shell theory, only this first term 1 plus zeta by R1 is this, and this taken is only 1 in the case of inverse. And some researchers have considered 1 minus zeta by R1 is also, and some other researchers have considered up to this. So, it is depending upon that, which is obvious that compared to 1, the contribution of these terms are less, but sometimes they may give more accuracy at the stresses required zone. So, if we are talking about a composite plates, in that case that researcher have considered the term up to zeta by R1, because in that at the interfaces the transverse stresses are there, bending stresses are there. So, we need to consider these terms. So, if you take up to second order, then it is considered as a Flige shell theory, and if you multiply with this, so ultimately you get the terms like this, that 1 minus zeta by R1 plus zeta by R2 minus zeta square R1 R2 plus zeta square R1 square, then you have to evaluate it through the thickness. So, if it is a isotropic cell or a single layer cell, though it may be a orthotropic material, but it is, if it is a single layer shell, then you have to integrate it. But now here we are talking about a composite cell which may have a n layers, number of layers. Then how do you evaluate it? So, in the case of n layer, it will be a layer wise, you have to do addition, that if the first term Q11, so Q11 will be the, at each layer the stiffness will be different. So, we will say that, let us say K goes from 1 to n. So, K goes from 1 to n, Q11 of K. K is that kth layer, let us say 1, 2, 3 and so on. So, very first we are talking about, let us say K is equal to 1, then this term. So, this integration will give you zeta times, and if you put the limits plus h by 2 to minus h by 2. So, the coordinates of top layer minus the coordinates of bottom. So, if there is one layer, let us say that is the kth layer, so coordinate of upper and minus lower. So, that gives you the thickness, ultimately it is the thickness of that layer, this term, thickness of that layer. Now, the second term zeta by R1. So, zeta, if you do integrate, it will come zeta square by 2, and then it will be zk plus 1 square by R1 minus zk square by R1, this is the term. And the third, same way this, and when we have a zeta square, then it will be a zeta cube terms will be there. So, in this way we can evaluate the effective coefficient of A11 for a case of multi-layered composite plate. So, whenever we are going to develop a solution for a multi-layered plate based on FSDT theory or a classical shell theory or any higher order shell theory, then we evaluate a effective coefficients, then adding through like this. So, what are these Q1K? Q1K is find it out in terms of stiffness in that direction, 1 minus mu12K, mu21K. These relations are given in books of composites, but for ready reference I am presenting here Q12, Q22, Q66. So, a composite shell may have any layers, and for a cross ply it may have 0 degree, 90 degree, 0 degree, 90 degree and so on. What is the concept of Zk and Zk plus 1? Let us say we are giving a number 1, 2, 3, 4, 5 up to n, and in between kth comes. So, for a kth layer this will be the bottom coordinate and this will be the top coordinate. So, above that there will be k plus 1th layer and here will be k minus 1th layer. So, this will be Zk and this will be Zk plus 1. These are the standard procedure one can use, even whatever we have used for a plate or a beam. So, for a composite concept these are same things, Zkth layer. Or in the case of, if you talk about, it will be instead of thickness, generally we decide the thickness of a shell is minus h by 2 to plus h by 2. So, that can be also thickness can be find it out. Now, let us say we have defined that constitutive relations, and first we will solve for a static case, and definitely first we will try for a linear governing equations and all static terms are 0. So, in the shell theories, even after developing the basic governing equation, we can further simplify, means solution of that. That first one is the membrane theory of cell and second is the moment theory of cell or a fluxural theory of cells. So, why we need the separate treatments? The reason behind that, anyway we can solve a problem altogether, but that will be a more complex. So, if we say that if a loading and boundary condition are such a that it comes under the assumptions of membrane theory of cells, then we will apply the concept of membrane theory of cells. The idea is behind that thin shell is very thin and it is subjected to only in plane stretching, there is no bending moments. So, moments M11, M22 and M12, M21 are 0. If we assume this condition, because we say that it cannot take a bending moment, only the stretching in plane it can take. So, this equation basically number 3 equation and number 4 equation, if you put all 0, then Q1 becomes 0, and here also if you put all 0, Q2 becomes 0. So, 3 and 4 equations become identically 0, and from that Q1 and Q2 gives 0. So, from there if you use in the 5th equation, that gives you only N11 upon R1 minus N22 upon R2 minus Q3 equal to 0, the third equation. Now, if we substitute in the first and second, that will give you these 3 equations. So, depending upon a situation or a requirement, we can apply. So, now you see that number of governing equations are reduced plus number of variables also have been reduced. Now, we have variable N11, N22, N21 and N12. So, again depending upon the cases, we can say that our variables will be also 3 later on, that some terms will be 0 going to be and that equations will be 3. So, membrane state of stress that cannot support the bending and twisting moments, then corresponding theory is also basically that theory is the thin shell theories, in which we assume that there is no bending moments. Now what are the necessary and sufficient boundary conditions? When we concept is it when we are going to apply this membrane theory of cells. So based on your careful examination, suppose some work come to you, research work you are going to do, or you are going to solve a problem, let us say in the case of fluid filled structure, like you have a very big cylinder or in which the oil is filled and it is buried inside the soil. So or it is just carrying a vehicle is like LPG storage tanks, na? Through a trailer it is moving. So you want to know that stress is in that shell, or let us say some aerospace is moving and their body of shell you want to study. So basically when do you analyze those shells under membrane theory of cells? Very first case, the boundaries means the very first condition, the boundaries of a shell free from transverse shear forces and moments. जो आपकी बाउंड्रीज है जहाँ पे वो शेल सपोर्टेड है, दैट शुड बी फ्री फ्रॉम एनी मोमेंट एंड shear forces. So generally the simply supported one is most ideal situation. In the simply supported one we may have no moments, but we may have that shear forces because at that boundary. So the free boundaries, no moments, no shear forces. Then the loads applied to the shell boundaries must lie in the plane that are tangent to the middle surface. So loads should be applied in such a way they lie in the plane of middle surface, so that they cause a pure stretching effect in the shell. They do not cause bending effect. The next condition is that normal displacement and rotations at the cell edges are unconstrained, means they are allowed to move. That is, their edges can displace freely in the direction of normal to the middle surface. So that it should be, boundary condition should be applied in such a way that the W, which is the transverse deflection, it can have the transverse deflection, it may allow to move in that direction. Cell must have a smooth, varying and continuous surfaces. If there is a breakup in curvature, if there is abrupt changes in the dimensions or the curvature, then their moments may arise. So we cannot apply those concepts. And then the component of the surface and edges load must also smooth and continuous function of coordinates. So if we talk about a, let us say a structure, so or inside that there may be some disruption is there. So these are the points where curvature changes, and then where are some sudden changes in the thickness or some boundary conditions clamped, so it may have stresses. So there we cannot apply the solution. So we cannot say that the membrane theory of stresses will be applicable to those conditions. So it should be a continuous like this. So in this zone the membrane theory of shells can be applied. Now we are going to in next lecture perform that membrane theory of stresses. I will explain one or two examples taking the circular cylindrical shell. So first we will convert using this concept that longitudinal axis our alpha is x, beta is theta, and A1 is 1, A2 is R, R1 infinity, R2 R. We will first convert these three equation into a cylindrical equation, and depending upon the loading and other boundary condition we are going to solve these equations. Thank you very much.